Okay. Lab this week is the magnetic field of a solenoid. And for a solenoid, let me grab what we're using. Solenoid is just a fancy name for a coil of wire. We use the term solenoid, we use the term inductor. I don't know, we have a lot of names for a coil of wire. But in this lab, we're just going to use our old favorite toy, the slinky. It's made out of metal, so it's conductive, and it's in the right shape, and it's easy to change the length, and it's easy to change the number of coils. So that's what our solenoid is going to be this week. The video is pretty clear on the setup. When we run a current through a wire, it fills the space around it with a magnetic field. And the magnetic field encircles the wire. So if the wire is coming toward you, toward the camera, the magnetic field forms circles around the wire. I could draw that here. So here's if the current is coming toward us here, with magnetic fields, you have to be able to draw in 3 dimensions because the current is in one direction, right? And it's toward the camera, and the plane of the magnetic field is perpendicular to that. So we have to be able to start drawing in 3 dimensions. One thing that helps is using the dots and X's. A dot indicates something is coming toward you. And the way to remember that is that it's like an arrow. If somebody shoots a bow and arrow and the arrow's coming toward you, what do you see? Just the tip of the arrow, right? Just a dot. But if it's going away from you, you see the feathers on the back that make like a crosshairs. So something coming toward you or out of the page has a dot. Something going away from you or into the page is an X like that. And so our magnetic field forms circles around. We use B for magnetic field. And in this case, it would go the opposite direction. So if you're standing over here with your magnetic field sensor, what direction does it point? Tangent to the magnetic field line. If you're standing over here, what direction does it point? The magnetic field points tangent to the field line. So given the fact that the magnetic field forms around a current carrying wire, and what is the magnetic field near a current carrying wire? It's proportional to the current. And it's inversely proportional to the distance. The farther away you are, the weaker it gets. It drops off as 1 over r. But it's proportional to the current. So now we're wondering what happens inside of a coil of wire. So a coil of wire So our magnetic field in the first case would look something like this. And if we look down the middle, the magnetic for the current is doing this. Current is doing that. And the magnetic field would be into the page in the middle. And it would be kind of coming back up around the outside like that. So it runs along the axis of the solenoid. It runs, it's easier if I do it this way. The magnetic field runs along the axis depending on whether the current is going one direction or whether the current is going the other direction. The magnetic field runs down the axis of this thing. And inside the solenoid, it's pretty uniform. The current is pretty uniform across the cross section of that solenoid. And outside, it's very weak. So we want to know what's the current at the center of that solenoid. So we get our magnetic field probe out. And we're going to stick it in. We've got our solenoid hanging there. Actually, it's going to be laying on a table, but you get the idea. Hanging there. And the probe is going to go in the middle. And it's going to measure the magnetic field. Now, the probe, if you had one in your hand, you'd see that there's two. It can measure a magnetic field that's going perpendicular to the probe, or it can measure a magnetic field that's parallel to the probe. We're sticking it in. We're trying to measure a magnetic field that's perpendicular to the probe, so we would set it to that. And it also has different gain settings. If you're measuring a very weak magnetic field, you can crank the gain up, but we'll just leave it on 1. And there's our magnetic field probe. We'll learn how these work in another couple of weeks, or maybe less. So this goes right into the center, right into the center. If you're looking down this way, the probe should be centered in the solenoid. We're looking at the magnetic field at the center of that solenoid. All right. The video is pretty clear. Yes, yes, this is a right-hand rule. We have a number of right-hand rules in physics, and one of them is on the direction the magnetic field forms around a current-carrying wire. You put your thumb in the direction of the current. So in the left here, the current is coming out of the page. I put my thumb out of the page. And my fingers, so if the current is coming toward me, I put my thumb toward me, and then my fingers kind of wrap around. I know the magnetic field forms circles around it. I don't know whether they go clockwise or counterclockwise. So when I put my thumb toward me, the wire, a current-carrying wire carrying a current toward me, would produce a magnetic field that curls this direction around the wire. For me, I would say counterclockwise. And when it forms toward you, I would say it's clockwise. You would say it's the opposite direction, right? All right, so what you want to do, the first thing you want to do is think about, well, what might affect the magnetic field inside of that solenoid? We know it depends on current, so let's start there. Varying the current will probably vary the magnetic field inside that solenoid. That's one thing we need to change. What else might it depend on? The length. So if I have a certain number of coils, let's say I have, I don't know what that is, 15 coils. and I make it longer or shorter, I change the density of those coils, don't I? And if it depends on current, if the magnetic field depends on the current and I decrease the density of the coils, I'm effectively reducing the effect of the current. So it might very well depend on length. And if I keep the length fixed, I can increase or decrease the number of coils in there, right? I can add more coils or pull some out, all while keeping the length fixed. That might have an effect also. So those are probably the three main things. If you can think of something else, great. But those are the three things that I came up with, and that's what I tested when I set it up. So I set up the experiment, I varied the different items, and I created a data file. The only tricky part here is that we use this probe is made by a company called Pasco, and they have special interface boxes that these plug into that help the computer figure out what the signal means. And they have their own proprietary software for running all of that, recording the data, extracting the information from the graphs we have, stuff like that. So I used their software. I created a data package with all the runs. I put that online. That means you have to download their software to open up the data and analyze it. They allow you a 60-day free trial, so you just download it to your computer. The link is in the handout that's posted. Go to pasco.com, the link is there, downloads. You need Capstone is the software that you need. It shouldn't ask you for any information. It should just download and work properly. And at the end of 60 days, it'll tell you, you can't use this anymore. You have to put in a key, the license key. And unless you have one, then it's not going to work anymore for you. So that's the story with that. So download Pasco Capstone software, download the data file that's also linked. It's on my website. You'll need those two things. There's also the lab write-up, and the lab write-up has a link to a video where I show you how I take the data and how I use Capstone software to extract the data and all of that. So you're trying to come up with the equation. You're trying to come up with this. B is equal to something, right? So if you decide that B is proportional to I squared, then you're going to have an I. Let's do one at a time. This is the goal, right? So you do an experiment. You're going to vary the current. Well, actually, I varied the current. You're going to analyze the data, and you're going to come up with the fact that B is proportional to something. Let's pretend it's I squared. May or may not be. Then you're going to say B does not at all depend on something. What should it depend on? L. Doesn't depend on L. So and then B is proportional to N, maybe, something like that, okay? So if B is proportional to I squared and B is proportional to N, then B is going to equal N times I squared times something, right? Your goal is to determine this equation, right? If B is proportional to A and B is proportional to B, then B is proportional to A times B, right? We know that. And then see if you can figure out what that constant is. So see if you can come up with the whole equation for the magnetic field in a solenoid, how it depends on each of our variables, N, the number of turns, L, the length, I, the current, and see if you can figure out what that constant is out in front, that proportionality constant. I don't think I have anything else to say about today's lab. It's the video's pretty complete. I talk about how the experiment was done and how the data was collected. And then I talk about the software, Capstone software, how you use that. Maybe I'll just go over that one more time here. And then I talk about how I use Excel to plot the data. So in Capstone, you're going to get a file that you don't know what it looks like. It looks like this. It's going to be magnetic field versus time. And it's going to look something like, most of them look something like this. 0. Most of the files look something like this. When I start it up, it gives you some weird reading. The sensor hasn't been zeroed recently. It just gives you some stray reading. So you just ignore this. What I did here, I hit the tear. That zeroes the sensor. It doesn't go exactly to 0, but it's pretty close. It gets you close to 0. So this is background. This is what I call background magnetic field. Then I turned on the current in the solenoid. So this is the magnetic field caused by the solenoid, right? Caused by the current in the solenoid. Then I turned off the current in the solenoid, and it should go back to whatever magnetic field exists at this point in space without the solenoid being there, right? Just the Earth's magnetic field. I don't know what other magnetic fields might be in my room here, but mostly the Earth's magnetic field. And the reason I do that is because sometimes the reading drifts a little bit over time. You can see it's not really a horizontal line. It kind of drifts a little bit. So I just wanted to take a background before and a background after to see if I had a lot of drift in my sensor reading. But most of them I think are pretty good. They read the same before and afterwards. So I show you in the video how you do a measurement, how you select using their software package this region here. You want to select these two regions and exclude everything else and just get an average of the background magnetic field before you turn on the current. This is the magnetic field that exists due to the Earth and whatever else produces magnetic field in my room here. Then you want to take the background, then you want to move down to here and check, get an average magnetic field with the current on. Then you subtract them. It doesn't matter that we didn't start at 0 because we just subtract one from the other to get the difference. We want to know what magnetic field is caused by the current running through the coil of the solenoid. So we subtract the two, and I show you how to do that in Excel. My magnetic field came up as negative because of the way the sensor defines positive. So the sensor defines a magnetic field in one direction as positive, and because of the way I hooked up the leads to the power supply, my current was running in the opposite direction, and so it created a field that it calls negative. I could have switched them, I guess, but it doesn't matter. All I care about is the difference between the background field and the magnetic field when there's a current present. So I subtracted them. I subtracted the the measured value with the current on from the background because I wanted a positive number in the end, but it doesn't matter. All you care about is a difference between those two. remember, one of the values is positive and one is negative, and don't lose that negative sign. When you subtract, you're really adding, right? You understand? Here's 0. You start out, your signal is up here, and then it goes down here. And what do you want? You want this. You want this distance. This is what caused, that is the change. So when you subtract them, you need to keep the positive one is positive and the negative one is negative. So you're really adding them together, right? You're getting this total distance. Now, I did it the exact same way every time. That maybe my timing was a little bit off here or there, but every graph should look something like this: B and time, and there's a 0 here. Every graph should look about the same. It starts, sometimes I was doing them quick enough that the sensor wasn't drifting. So the signal was here. I would, after about 3 seconds, I hit the tare button. So sometimes you see a small change. And then I waited 6 seconds or so, let it stabilize. Then I turned the current on. Then I turned the current off. And then I went another 3 or 4 seconds, and then I stopped. So this region is always current on. And this out here, you can just kind of ignore. And then you're going to pick a couple of seconds on this side and a couple of seconds on that side to include for your background. But every graph should have that same appearance. And so you'll do the same analysis for each one. Anything else I wanted to say? I don't think so. Questions? So first thing you'll look at on my website is the handout. There's also a link on my website to the data file. And then in the handout, it tells you where to get the Pasco software. You're going to download the data file. You're going to download the Pasco software. And then there's a link to the video instructions as well. So a number of links there that are important. The video instructions, I think, will show you. Once you see how the experiment's taking place, it'll be more obvious to you as to what the data means. And like I said, I follow the same procedure each time. And your job is to determine this, where did it go? Disappeared. What the magnetic field is, B is equal to what? And I want to know the constants and whether it's there's an I and an N and an L in here, and if they're squared or if they're just linear, or how do they go? You know what I mean? We can do the report Sunday evening. Sunday evening. All right, I think I'm going to stop the recording. I will stick around if you have questions.